This is me about a year ago. It's 47 degrees Celsius. Around me are tunnels that stretch into complete darkness. There's 1.5 kilometers of rock above my head, and above that is the North Sea. I'm going to explain why I was there and why this place matters. So, as we've just heard from Stuart and from Miles, we're going to need to deal with billions of tons of CO2 emissions from ongoing industries. And that's going to be really challenging. Now, I think when a lot of people think of that process, as Miles already alluded to, I think they think of trees and nature doing a lot of that offsetting work. And whilst this is absolutely vital, and Alini is going to talk about this later, it cannot bear the burden alone. And it's already under stress from climate change. And so we're going to need something quite different. We're going to need this. We're going to need industry, carbon capture, and permanent geological storage. So I'm a geophysicist. I work on studying the Earth's subsurface to solve problems related to this industry, to work out how to make sure that CO2 stored geologically deep underground stays there for a very, very long time. Explaining one of the most fascinating parts of my job, right now at least, starts here, though, at the surface. So this is the Bolby Mine. It's a relatively unassuming industrial site on the North Yorkshire coast here in the UK. But nothing really can prepare you for what's underneath this place. So since the 1960s, generations of miners have been extracting mineral fertilizer from deep underground, from thick layers of salts over 1 kilometre below the surface. They've excavated tunnels that lead tens of kilometres out underneath the coast in the North Sea. And there are now, through the network of tunnels, thousands of kilometres of tunnels, all interconnected, covering a vast area of rock. These rocks and the salts here extend out across the North Sea into the same areas where CO2 storage is being developed right now in the UK, in the southern North Sea and beyond. Beneath those salts are sandstones. These are porous rocks filled with microscopic little bubbles and spaces that you can think of as acting a lot like a sponge. These sandstones are the same kinds of rocks that once held for millions of years oil and gas, and now we're getting them to store CO2 instead. I think when lots of people think of geological CO2 storage, if they don't know about it already, would imagine sort of pumping CO2 gas into big caves underground. And that's just not what's happening here. What we're actually doing is injecting liquid or very dense supercritical CO2 into the sandstones, filling them up and it getting absorbed like water into a sponge, and then it stopped being propagating up to the surface, going up vertically, by impermeable rocks, thick layers of impermeable rocks, like salts above the sandstones. That way, the CO2 will stay trapped underground over geological timescales, just like it was for oil and gas. So hearing this, I think it's quite reasonable to ask, how do we know that this works? And the thing is, geological carbon storage really isn't new. So since the 1970s, the oil and gas industry have been injecting large quantities of CO2 into the subsurface. And for around 3 decades now, there have been dedicated permanent geological CO2 storage projects operating around the world, some of which are storing millions of tons of CO2 every year. We don't really think about that most of the time, but across all of these early projects, a lot of those common questions and common worries have been answered. So far from these projects, there has never been a leak of CO2 to the surface, and there have never been any earthquakes that anyone has felt that has resulted from that CO2 injection. The problem isn't whether this works, it's about scaling it up to vastly more than what it's doing right now and making sure that that's done safely. And that's where my work comes in. So I work on monitoring, on listening to the Earth, and as it responds to what we do to it. So as we inject CO2, the rocks move by tiny amounts, fractions of a fraction of a millimeter. And as they move, they make noise. These are tiny earthquakes, you can think of them like, that can tell us a lot about how these rocks are behaving. These are far too small for anyone to feel, these events, but not small enough for my instruments to detect. So what I'm doing deep underground in this really unique environment is deploying sensors and listening for these signals to better understand how fractures behave in these salts, how fluids can move through these environments, through these rocks, and to better characterize faults, geological faults, and their risks that they pose on CO2 storage. Doing this in this really unique, deep environment is extraordinary and incredibly rare. We get to walk through massive amounts of rocks that would otherwise be buried kilometers deep and uncover a bunch of the uncertainty that would otherwise be clouding our view. So this is a really extraordinary place to do work. The thing is, it's not just about better science, it's about better decisions. So this work that I do relates to the way that we regulate CO2 storage, the way that we decide what's acceptable, what's safe, and what to do if something goes wrong. Now, for this kind of work doesn't happen in isolation. It has to come at the intersection of science, of regulation, of industry, of governance, and of public trust. And that kind of intersected work is exactly what Oxford Net Zero was set up to do. And it's what makes Oxford Net Zero a really unusual and really special place to do work. The thing is, the reason why that intersection is really important is because carbon storage is one of the industries where trust matters as much as the technology. Because if a project goes wrong, it won't just be that one storage site that we may lose. We could lose trust in the entire endeavor, and then we could lose public confidence and trust in one of the most vital tools that we need to stop climate change. And my work helps to make sure that that doesn't happen. So my fellowship at Oxford Net Zero allowed me to take this idea seriously. It gave me the space and time to really push the frontier of this underground science. It allowed me to apply for and win more funding to do early experiments, to set up now a global network of industry and academic experts trying to share the potential of this incredible place, and to really push this and to start the work on turning this environment into a global and national asset for energy transition research. So the science I work on really tries to make sure that that CO2 storage industry can expand safely, responsibly, and with that public trust. Like, the work that I do doesn't just study the Earth, it helps to make sure that the rocks beneath our feet will be there to help protect the climate above them. Thank you very much.